Subscribe to the channel and hit the bell. Welcome back to another explainer from What Did the Code Say? I'm Dragon Megalodon, and today we're tearing apart the underlying logic that drives predictable patterns and completely runaway loops in mathematics. We're going to translate the raw syntax of polynomial and exponential functions just to see exactly what makes them tick.
So here's the ultimate problem. What actually determines how a mathematical system behaves when you push it to infinity, right? If you want to predict how a system acts at its extreme limits, you absolutely have to understand the fundamental algorithms governing its growth. But before we can compile any crazy exponential loops, we first need to parse the static scripting language of mathematical models, which are polynomial equations.
Section 1. The Polynomial Syntax.
Think of a polynomial as your basic, static script for a predictive model. The very first parameter you've got to check is the degree. The degree is, simply put, the largest exponent in the entire equation. For example, if your highest power is a 4, boom, your degree is 4. This single number is critical because it dictates the overall potential of the curve, drawing the hard boundaries of exactly how it operates.
Now, you might be wondering, what actually powers that degree? Well, that'd be the leading term and the leading coefficient. The leading term is the specific block of code holding that highest exponent, and its numerical multiplier is the leading coefficient. Think of this multiplier as the engine driving your algorithm's output. And hey, quick pro tip here, this term dictates the main logic even if some messy programmer writes it at the very end of the code snippet. Remember, the highest power always takes the steering wheel.
On the flip side of that, we have the constant term. This is your standalone number with absolutely zero variables attached. You can think of the constant term as your absolute baseline data point. It's this completely isolated, stubborn anchor that remains unchangeable no matter what kind of wild variables you input into the system.
Okay, let's patch a really common beginner bug right now regarding turning points. Turning points are exactly what they sound like. They're local, extreme changes where the graph completely flips direction. Now, you might have heard somewhere that the number of turning points is always just the degree minus 1. Absolutely false. The actual rule is that the turning points are strictly less than or equal to the degree minus 1. So a degree 4 polynomial algorithm has at most 3 turning points. But depending on the specific syntax, it could honestly just have 1. So keep that logic in check when you're graphing.
Section 2. Predicting end behavior.
All right, now that we understand the basic syntax, we can actually forecast extreme outputs without having to compile the whole script. It's like a shortcut. Just 2 variables, whether the degree is even or odd and whether the leading coefficient is positive or negative, act as logic gates to completely predict the graph's endpoints. If the degree is even and positive, like x squared, the graph rises to the left and rises to the right. If it's even and negative, both sides fall. If the degree is odd, the ends point in totally opposite directions. If you master these 4 basic gates, you can instantly read end behavior.
Section 3. The Exponential Algorithm.
We're shifting gears now from static limits to a much more aggressive syntax, exponential functions. Let's visually contrast a rigid polynomial structure, something like f of x equals 3x, where the variable x is just a standard multiplier, with an exponential base. Injecting that variable x directly into the exponent, that creates an explosive compounding loop. Let's deconstruct the parameters of this new syntax.
In our new exponential algorithm, a represents the initial value. This is your y-intercept, basically ground 0, the exact starting data point when time, or x, is 0. Then we have b, the base. This is the multiplier that determines if our system is going to scale up or shrink down. If b is greater than 1, the function is increasing. It's getting steeper. If b is a fraction between 0 and 1, the function is decreasing. And we've got some hard rules to prevent the code from just completely crashing. B cannot be 1, b must be positive, and a cannot be 0, otherwise the whole system just flatlines.
Section 4. Coding exponential growth.
Let's actually compile this code using some real-world data, starting with predicting a salary trajectory. Step 1. You land a job with a $40,000 base salary. Step 2. You lock in a guaranteed 3% annual raise. To calculate year 1, we simply multiply 40,000 by a growth factor of 1.03. Step 3. Year 2 compounds on the previous year, so we multiply by 1.03 again. Step 4. We finalize our general algorithm. The salary after t years is 40,000 times 1.03 to the power of t. Plug in 5 for t, run it, and your console outputs $46,370.96. Not too bad.
We can actually deploy this exact same architecture for macro data. Take the United Nations. They estimated a 2010 global population baseline of 6.79 billion people, growing at about 1.1% annually. So, Our initial value A is 6.79, and our growth factor B is 1 plus 0.011. That gives us our algorithm f of t equals 6.79 times 1.011 to the power of t.
Now watch this. If we run this population code forward for 40 iterations, meaning 40 years to the year 2050, the model outputs a massive 10.5 billion people. That right there is the sheer, unstoppable power of compounding exponential loops.
Section 5. Debugging exponential decay.
So let's analyze what happens when a logic reverses, causing our underlying data to shrink in a process we call exponential decay. The base b is still our multiplier. For growth, you add the percentage rate r to 1, but for decay, you just subtract it from 1. It's a really simple syntax flip, but it completely inverts the output from a massive upward spike to a steady downward curve.
Let's track this by looking at the metabolism of a drug called Seroquel. Step 1. Your initial dose is 400 milligrams. Step 2. It gets eliminated from the body at a steady rate of 11% per hour. Step 3. We calculate our shrink factor by subtracting 0.11 from 1, which gives us 0.89. Step 4. Compile the final code. F of t equals 400 times 0.89 to the power of t. If we execute this over 24 hours, the system calculates that only 24.4 milligrams remain in the body. It just steadily decays away.
Once you recognize these patterns, you can read complex financial models instantly, like you're reading the Matrix. A Toyota Prius valued at $3,000 times 0.95 to the x immediately signals a 5% annual depreciation, simply because 0.95 is less than 1. Compare that to an antique car valued at $50,000 times 1.07 to the x. That 1.07? That indicates a very nice 7% compounding appreciation.
Let's lock in this pattern recognition one last time with some biological data. A Petri dish bacteria algorithm reads 12,000 times 1.45 to the x. A base of 1.45 means you've got a volatile 45% biological spike happening every single hour. Meanwhile, a salamander population algorithm reads 3,000 times 0.78 to the x. A base of 0.78 clearly indicates a 22% population crash year over year. The numbers literally never lie once you know how to read the syntax.
Polynomials use degrees to set rigid boundaries, while exponentials rely on dynamic bases to power infinite loops of growth and decay. If you want to understand what the code says before it explodes, hit subscribe. Don't forget to like. This tells YouTube that technical content is still alive. Share this with a beginner coder who needs help. And what did the code say in your project today?